The beautiful thing about the Reidemeister moves, remember the Reidemeister moves were the three ways of modifying a knot diagram that change the diagram but do not change the knot that that diagram represents. They all correspond to isotopies of that knot. The type 1 move, the twist, the type 2 move, the poke, the type 3 move, the slide. These, Reidemeister proved, are the only three ways of changing a knot diagram that correspond to isotopies. In other words, do not change the knot in three-dimensional space. And what's great about that theorem is because we know any two diagrams of a given knot are going to be related by those Reidemeister moves. What that also tells me is that a knot invariant can be told to be a knot invariant if and only if that property is preserved by each of the three Reidemeister moves. If none of my Reidemeister moves can change the value of my knot diagram property, then no difference in diagrams for the same knot can change the value of that property. So to check whether a diagram property is a knot invariant, all I have to do is check to see whether that property is preserved by each of the three Reidemeister moves. If it's preserved by all three Reidemeister moves, it's a knot invariant. If it's not preserved by even one of them, then it must not be a knot invariant. So let's return to the examples that we just did in the previous activity. And the only candidate that we have for an invariant so far, the difference between the number of overcrossings and the number of undercrossings in a complete trip around the diagram. Let's see if we can determine whether or not that is a knot invariant. So we just need to check and see if that property remains unchanged under a type 1 move, a type 2 move, and a type 3 move. And so we want the total number of overcrossings minus the total number of undercrossings. The number of over minus the number of under. This is my candidate, maybe a knot invariant. All right, so let's imagine that I have a knot with some diagram. Who knows what it's doing? Yada, 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 yada. Yeah, whatever. So I have some diagram of a knot, and then maybe I just make one little extra bend over here. All right, so here's some nasty looking diagram for a knot. And let's say that the number of overcrossings minus the number of undercrossings is some number. Let's call it n. I don't know what it is because I don't know what this knot is because I just drew a scribble on the board, right? Now let's apply a type 1 Reidemeister move to this diagram and see if this value changes. So that's the name of the game here. I'm just going to zero in on this part of my knot over here and imagine what happens if I just apply a twist to it. So now I've applied a type 1 Reidemeister twist to my diagram. Have I changed the number of overcrossings minus the number of undercrossings? So I'm over here, I'm doing a total of n over, the amount by which overs exceed unders is actually n over here. And then I emerge, I come over here, I find that I get one more overcrossing, but then as I'm coming back around on this same arc, I get another undercrossing as well. So a type 1 Reidemeister move is going to add an overcrossing in this invariant, but it's also going to add an undercrossing. And so the difference between overs and unders, if the old difference was n, the new difference is also n. Right? Because I've added one to the overs, but I've also added one to the unders. And so the difference remains the same. So it passes the type 1 Reidemeister move test. Right? The type 1 Reidemeister move does not change the amount by which the overcrossings exceed the undercrossings. How about type 2? Same process. We have some nasty diagram for a knot. Whoops, let me make sure it connects back to itself here. So here's my diagram. The number of overs minus the number of unders is n. Now it's our job to try applying a type 2 Reidemeister move to this diagram and see if that difference, overs minus unders, changes. So I'll just take this piece of the diagram and I'll just do the poke maneuver where I'll take this piece of the diagram and I'll just sort of put it underneath on that side. So I've just done a type 2 Reidemeister move to this diagram. What can I say about the total number of overs minus unders? So in this part of the diagram, we have a bunch of overs and a bunch of unders. The difference between them is n. Then we emerge. We come along the diagram this way. We encounter an overcrossing. And as we keep going, we encounter a second overcrossing. So now we've increased the number of overs by 2. I double back. And now I encounter an undercrossing. So we increase the number of undercrossings by, we have one more undercrossing than we used to have. And then we have 2 more undercrossings than we used to have. And then we're back in the rest of the diagram. So doing a type 2 Reidemeister move to this diagram has increased the number of overcrossings by 2, but it's also increased the number of undercrossings by 2. And so the difference between overs minus unders is going to be the same after the type 2 Reidemeister move as it was before the type 2 Reidemeister move. So we've passed the type 2 Reidemeister move test, right? Type 2 Reidemeister moves do not change the amount by which the overcrossings outnumber the undercrossings, because we're going to be adding overs and unders in pairs when we do a type 2 move. All right, let's do the type 3 example. If it passes the type 3 test, then we know that we must have a not invariant. If it fails the type 3 test, then we don't. So let's do type 3. We have some nasty knot diagram over here. And then I have a crossing and, you know, something going on over here where I have a strand that goes kind of under both of these. And then we loop back into here, right? So I'm trying to set myself up so that I can use a type 3 Reidemeister move. And in order to use a type 3 Reidemeister move, I need to be able to have sort of a crossing, the green and the blue strands here, and then another strand that's underneath the whole thing, or possibly above the whole thing, right? So that's how I've kind of tried to create the 3 crossings that I've pulled over to the side here. So we start with n more overcrossings than we have undercrossings in my entire diagram. And then I'm just going to take and apply my type 3 Reidemeister move to this. And when I do that, let me just sort of try and draw these both on the same diagram and see if it makes sense. So I'll have my new diagram, which kind of comes over this way instead. And then rejoins over here. So in my original diagram, if I sort of take this off ramp and continue over this way, I had an undercrossing and then a second undercrossing, and we came back around to an over, under, and continue. If I took the other fork instead, so after my type 3 Reidemeister move, I'm still encountering an under, followed by another under, followed by, if I rejoin this, I'm going to encounter another under and so forth, and I'm going to end up being back into the original. So I believe I'd have to probably, I think this diagram is maybe not the best diagram to convince you, but I believe that we're still okay. I believe that the amount by which overcrossings outnumber undercrossings is the same before I did this type 3 move compared to before I did this type 3 move. And if that's the case, then this property is a not invariant. But you might want to double check my work on this type 3 move, because for some reason, I'm second guessing myself. So this is the great thing. The fact that all the different diagrams for a given knot are all related by Reidemeister moves is what gives us a way of checking all infinitely many diagrams for whether or not they're all going to tell the same story. If you give me a property of diagrams that remains the same under each of the 3 building blocks of Reidemeister moves, the type 1, the type 2, and the type 3 move, if it passes all 3 of those tests and remains the same under each of those 3 moves, that guarantees that it's going to remain the same for any possible diagram that we could ever sketch of that knot, and therefore will be a not invariant.